Hello everyone. So, in last class we derived the laminar boundary layer equations for natural convection over a vertical plate. We derived continuity equation, y momentum equation and energy equation. So, we have three partial differential equations. In today's class we will use similarity method and we will convert these three partial differential equations to ordinary differential equations. Let us write down the governing equations whatever we derived in last class in non dimensional form. So, if you see that we have derived in last class, continuity equation is del u by del x plus del v by del y is equal to 0. Then we derived the momentum equation as u del v by del x plus v del v by del y is equal to nu del 2 v by del x square plus the boundary term g beta t minus t infinity, and also we have energy equation u del t by del x plus v del t by del y is equal to alpha del 2 t by del x square. So, if you know that we have considered vertical plate, okay, and this is your x and this is your y. In x direction we have velocity u and y direction we have velocity v. Ambient fluid is quiescent and it is having temperature T infinity. We have gravitational acceleration in negative y direction, that is g, and this wall is maintained at uniform surface temperature, that is your T w. So, now we will choose two reference scale, one is for length and one is for velocity. Let us choose that your reference velocity is u ref. Okay. We do not have any free stream velocity in this case. So, we are choosing some reference velocity, that is your u ref, and reference length let us choose h, okay, where h is the height of the plate, okay, or you can choose any other reference length. Now, we will use these non dimensional parameters. X star is in the non dimensional x coordinate, x by h, y star y by h, then u star u by u reference, v star v by u reference, then temperature will take T minus T infinity divided by T w minus T infinity. So, with this, now if you put it here and if you rearrange, you will get the non dimensional equations, non dimensional equations, okay, as del u star by del x star plus del v star by del y star is equal to 0. Then we have u star del v star by del x star plus v star del v star by del y star is equal to 1 by Reynolds number you will get here based on h or any reference length h, del 2 v star by del x star square plus the boundary term. So, boundary term, if you put all these things and rearrange, you will get g beta T w minus T infinity into h divided by u reference square into theta. Okay. So, using these non-dimensional parameters, you put all those things in the momentum equation, then if you rearrange, you will get the equation in this form, where in the viscous term you will get 1 by Reynolds number, and the buoyancy term you will get like this. So, we will simplify it later. First, let us write the non-dimensional energy equation: u star del theta by del x star plus v star del theta by del y star is equal to, you will get 1 by Reynolds number into Prandtl number del 2 theta by del x star square. Okay. So, if you see this term, okay, in the buoyancy term, so if you rearrange it, you will get g beta T w minus T infinity into h by u reference square. Okay. So, we will write in this form. Okay. So, we will write nu square by u reference square by h square. So, you can see this will give 1 by Reynolds number square into, now we have g beta T w minus T infinity. So, we have divided by h square here. So, let us multiply in the numerator. So, you will get h cube, okay, and now nu square we have multiplied in the numerator. So, you put it in the denominator. Okay. So, this term is now one another non-dimensional number, that is known as Grashof number. Okay. Grashof number. So, how Grashof number is defined? Grashof number is the ratio of buoyancy force to the viscous force, because in the numerator you can see this is coming from the buoyancy force, and in the denominator nu is there. So, it is coming from the viscous force. So, Grashof number is the ratio of buoyancy force to the viscous force. So, and it is written in this form: g beta T w minus T infinity into h cube by nu square. Okay. So, Grashof number based on h. Okay. So, now you can write this term. Okay. So, momentum equation you can write as u star del v star by del x star plus v star del v star by del y star is equal to 1 by Reynolds number based on h del 2 v star by del x star square plus, okay, so it is, you can see it will be Grashof number, and in the denominator we will have Reynolds number square. So, Grashof number divided by Reynolds number square into theta. So, this is your momentum equation. So, here we will define another non-dimensional number, which is your Grashof number by Reynolds number square, and it is known as Richardson number. So, this is known as Richardson number and denoted as Ri is equal to Grashof number divided by Reynolds number square. Okay. So, this Richardson number has physical significance, that it compares which force is dominant, buoyancy force or your inertia force. Okay. So, Richardson number okay. So, this is your Ri, Grashof number divided by Reynolds number square. Okay. So, you can see Richardson number. So, it is kind of buoyancy force to the inertia force. Okay. So, if it is so, now you can see three different cases. If Richardson number is much greater than 1, so what will happen? So, if Richardson number okay, much greater than 1. Okay. So, now you can see that Richardson number is much greater than 1, that means Grashof number will be much greater than Reynolds number square. So, what does it mean? It means that buoyancy force will dominate. Okay. So, in that case obviously buoyancy force is dominating, then you can consider that it is natural convection. Okay. So, that means it is having the natural convection. Okay. So, that means forced convection effects may be neglected. If Richardson number is much less than 1. Okay. So, in that case you can see inertia force will dominate. Okay. So, that means it will be forced convection. So, it will be forced convection. Okay. So, in this case your natural convection effects may be neglected. Okay. And if Richardson number is equal to 1, then what will happen? Your buoyancy force is comparable to inertia force. So, you cannot neglect either buoyancy force or inertia force. Okay. So, you will have both natural convection and forced convection, and that is known as mixed convection or combined convection. So, for Richardson number 1, okay, so you will get mixed convection, which is known also as combined convection. Okay. So, in this case you need to consider both forced and natural. So, you can see this example. So, if natural convection is happening, say you have a sphere, hot sphere, then Grashof number by Reynolds number square, which is your Richardson number, will be much greater than 1. L is the any characteristic length. So, in this case you will have only natural convection. So, due to buoyancy you can see you will have a plume and it will go up. Now, if Richardson number is much less than 1, then natural convection can be neglected and you have a forced convection. So, you can see this velocity is generated using some fan, and over this hot sphere this flow will takes place and heat transfer will takes place, and that is your forced convection. But if you have Richardson number is equal to 1, then you will have both natural convection and buoyancy effect will be there. So, in this case G is there and also in this case G is there. So, obviously you can see you will have buoyancy effect. So, this plume will go up, but you have forced convection also in the x direction. So, you will see the plume is go up in a inclined manner. So, it is known as mixed convection. Now, from here you can see that if you choose the velocity scale in such a way that the coefficient in the buoyancy term in the theta will become 1. So, in that case you can see, because reference velocity is arbitrary, right. So, it can be chosen to simplify the form of the equation. So, it is convenient to choose u reference square is equal to g beta T w minus T infinity into h. Okay. So, that your the term with the theta. So, you can see this term. So, if u reference square is g beta T w minus T infinity into h, then this will become 1. Okay. If it becomes 1, then obviously it is kind of Richardson number will become 1, and for this case you can see your Reynolds number square will be Grashof number, right. That is we have already defined, because this is your ratio, right. Richardson number Grashof number by Reynolds number square, and Reynolds number will be just root Grashof number h. So, you can see that Grashof number plays the role same role in the natural convection what Reynolds number plays the role in forced convection, right. Now, let us use similarity transformation method and convert this 3% differential equation to ordinary differential equation, so that we can have the numerical solution. Now, you can see in last class we have found scales for different quantities like thermal boundary layer thickness, then velocity v and also Nusselt number, and those are tabulated in this table. So, you can see for Prandtl number much greater than 1, the boundary layer thickness delta t is order of h r h to the power minus 1 by 4, and also velocity scale alpha by h Rayleigh number to the power half, and Nusselt number is order of Rayleigh number to the power 1 by 4. And you can see that the velocity looks like this. So, because at the wall you will have 0 velocity, and at the edge of the boundary layer we will have 0 velocity. So, your maximum velocity occur in between this boundary layer, and this is known as wall jet velocity profile. So, you can see at different location you will get this type of profile, and if you can say, if you see at this location, let us say it is y 1 and this is your y 2. So, you will get some profile like this, okay. And you can see that if you scale down this velocity profile with a proper scale, then you can bring down to this profile. So, that means if somehow we can convert this partial differential equation to ordinary differential equation using some scale factor, then your similarity transformation exists, and we can write this partial differential equation to ordinary differential equation. So, now how to choose this similarity variable? So, you here in the table you can see that we have this delta t, which is order of h r h to the power minus 1 by 4. So, this scale we can take for the similarity variable eta, and we have also velocity scale alpha by h r h to the power half. So, what we can do, you can, so this similarity variable eta, similarity variable eta can be constructed as x divided by any of these length scales, okay. So, we can use this delta t. So, we can write for Prandtl number greater than 1, okay. So, thermal boundary layer thickness, you can see delta t is order of h r h to the power minus 1 by 4. So, we can write eta as x by delta t. So, you can write, so this delta t we can write also y into r a y to the power minus 1 by 4. So, in this case we can write x by y r a y to the power 1 by 4, okay. So, it is in the numerator we have written. So, we are written plus 1 by 4. So, here Rayleigh number is defined as g beta delta t is your t w minus t infinity and y cube divided by alpha nu, okay. So, now you can see theta, okay, which is function of eta as well as Prandtl number, okay. So, this also we can define as t minus t infinity divided by t w minus t infinity, okay. So, in this case you can see this is the temperature profile, and this also you can use some scale factor, so that it will become same or all the temperature profile will collapse if you plot it with eta. So, theta you can write this way, and we know the vertical velocity scale as v order of alpha by y. So, this we are using r a y to the power half, okay, for Prandtl number greater than 1, this we are considering, okay. So, this we can write velocity scale v is equal to alpha by y Rayleigh number y to the power half into some constant. Okay. So, that is, let us say, capital F, which is function of eta and Prandtl number. So, this is your dimensionless similarity profile of the wall jet. So, this scale we can use, and we can now find what is the value of psi from this expression. Okay. So, now we will use eta is equal to x by y r a y to the power 1 by 4. Okay. And if you put the value of r a y, then you can write in terms of y as x g beta delta t is t w minus t infinity alpha nu to the power 1 by 4 y to the power minus 1 by 4. Okay. So, now you can find del eta by del x. Okay. So, it will be just 1 by y r a y to the power 1 by 4, and del eta by del y will be x g beta delta t by alpha nu to the power 1 by 4. So, now y to the power minus 1 by 4. So, it will be minus 1 by 4 into y to the power minus 5 by 4. Okay. So, now you rearrange it. So, here if you put y cube, so it will be y to the power 3 by 4. So, that you can put it here, and then you can simplify it, and you will get del eta by del y as minus eta by 4 y. Okay. After simplification. Now, we have v. So, v we have written as alpha by y Rayleigh number to the power half f, which is function of eta and Prandtl number. Okay. Now, we will find the stream function from this velocity v, and once stream function is known, then you will be able to calculate the velocity u and velocity gradient like del v by del x, del v by del y, and del 2 v by del y square. So, now let us find what is stream function psi. So, you can define v is equal to minus del psi by del x, right. So, if v is minus del psi by del x, so if you put it here, you will get, so this you can write minus del psi by del eta into del eta by del x. So, del eta by del x already we have found here. So, you can write minus del psi by del eta into 1 by y r a y to the power 1 by 4. So, now if you put this, so you can find del psi by del eta now into 1 by y r a y to the power 1 by 4 is equal to alpha by y r a y to the power half with a minus sign is equal to minus sign f. Okay. So, now if it is so, now you can write del psi by del eta is equal to, so this y will get cancelled. So, you will get minus alpha Rayleigh number to the power 1 by 4 into f. Now, you can integrate it. So, integrating, you can write psi is equal to alpha into Rayleigh number to the power 1 by 4 integral minus f d eta. Okay. And the integration constant is put inside this integral. So, now we will define a new variable small f, so that your d f by d eta will become minus f d eta. Okay, because f is unknown function. So, that we are writing in terms of d f by d eta. So, if it is so, now you can write psi is equal to alpha Rayleigh number to the power 1 by 4. So, you can see from here f will be just integral minus f d eta, and integration constant is involved here. So, you can write f, which is function of eta and Prandtl number. So, now we have found the stream function psi. So, you will be able to calculate the velocity u, right. So, here just let us write del eta by del x, whatever we have found, that is your Rayleigh number 1 by 4 to the power divided by y, and del eta by del y is minus eta by 4 y, and we have used f also as minus df by d eta. Okay. And von Mises transformation, again we will use it. So, let us write this von Mises transformation. So, in this case it is a vertical plate. So, we will use del of del x as del of del eta by del x, and for del of del y we will write as del of del eta by del y plus del of del y. So, we will use this transformation while finding the derivative. So, stream function we have found psi as alpha Rayleigh number to the power 1 by 4 f. Okay. And in terms of y, if you write, then you will get alpha g beta delta t by alpha nu to the power 1 by 4 y to the power 3 by 4 into f. Okay, because here y to the power 3 by 4 is there inside this Rayleigh number. So, that we have written outside. So, now velocity u you can write as del psi by del y. Okay. And del psi by del y if you write, then this transformation you have to use. Okay. So, if you use this transformation, you can see. So, del psi by del eta you can write alpha r a y to the power 1 by 4 f prime. Then we have del eta by del y, it is minus eta by 4 y plus, now you have del psi by del y. So, you can use it. So, alpha g beta delta t by alpha nu to the power 1 by 4. So, you have 3 by 4 y to the power minus 1 by 4 into f. So, if you rearrange it, so you will get minus alpha eta by 4 y Rayleigh number to the power 1 by 4 f prime, and the second term this y, now you put y cube you put inside, then if you rearrange you will get 3 alpha by 4 y Rayleigh number to the power 1 by 4 f. Okay. So, we have found the velocity u. Now, let us write the velocity v in terms of small f. Okay. So, in terms of capital F already we have written. So, you know that you have written v is equal to alpha by y Rayleigh number to the power half f, and this you can see f is minus df by d eta. So, you can write minus alpha by y Rayleigh number to the power half, and it will be f prime. And in terms of y, if you take y power, then you will write alpha g beta delta t divided by alpha nu to the power half y to the power half f prime. So, we are writing in this form because we need to find the derivative with respect to y, that is why we have taken y outside, so that it will be easier to integrate. Now, you can see in the momentum equation we have the velocity gradient del b by del x, del b by del y, and del 2 v by del x square. So, that let us find from this expression. So, if you use del b by del y, okay, so again this von Mises transformation, this one we will use. So, you can see it will be del b by del eta. So, that means minus alpha by y Rayleigh number to the power half. So, f double prime, okay, and del eta by del y. So, that is your minus eta by 4 y. So, here we have written. Okay. Now, we have del of del y, right. So, del of del y of this you need to write. So, it will be here one minus sign will be there. Okay. So, it will be minus alpha g beta delta t by alpha nu to the power half. Okay. So, now if you take the derivative of y, so it will be half y to the power minus half f prime. Okay, and if you rearrange it, so you will get alpha eta by 4 y square Rayleigh number to the power half f double prime minus alpha by 2 y square Rayleigh number to the power half f prime. Okay. Now, let us find the derivative of b with respect to x. So, that means del b by del x, you can write minus alpha by y. So, del b by del eta into del eta by del x. So, that will be Rayleigh number to the power half f double prime, and del eta by del x we have here. So, you can write Rayleigh number to the power half, sorry, Rayleigh number to the power 1 by 4 divided by y. So, if you simplify it, you will get minus alpha by y square Rayleigh number to the power 3 by 4 f double prime, and again del 2 v by del x square if you take. So, it will be minus alpha by y square Rayleigh number to the power 3 by 4 f double prime into again Rayleigh number to the power 1 by 4 by y. So, if you simplify it, you will get alpha by y cube Rayleigh number y f triple prime. Okay. So, now let us put all these in the momentum equation. What is your momentum equation? U del b by del x plus v del b by del y is equal to nu del 2 v by del x square plus g beta t minus t infinity. Okay. So, now if you put the value here, so first u, so this is your u. Okay. So, this if u if you put, so you will get minus alpha eta by 4 y Rayleigh number to the power 1 by 4 f prime plus 3 alpha by 4 y Rayleigh number to the power 1 by 4 f. So, this is your u. Then you have del b by del x. So, del b by del x is this expression. So, it will be minus alpha by y square Rayleigh number to the power 3 by 4 f double prime. Okay. Now, next term v into del b by del y. So, v is this one. So, it will be minus alpha by y Rayleigh number to the power half f prime. Okay. Now, into del b by del y. So, this is the expression for del b by del y. So, if you put alpha eta by 4 y square Rayleigh number to the power half f double prime minus alpha by 2 y square Rayleigh number to the power half f prime. Okay. So, left hand side the inertia terms we have written. Now, in the right hand side you write the viscous term nu into del 2 v by del x square. So, this is the expression. So, it will be minus alpha by y cube Rayleigh number f triple prime, okay, and we have the Buoyancy term. So, it will be g beta t minus t infinity. Okay. So, now we have theta is equal to t minus t infinity divided by t w minus t infinity. So, this term g beta t minus t infinity we can write g beta t w minus t infinity into theta. Okay. So, you multiply it first, then simplify it. Okay. So, this if you do, then you will get alpha square eta divided by 4 y cube Rayleigh number f prime f double prime. So, after multiplication we are writing these terms alpha square by y cube Rayleigh number f f double prime, then we have minus alpha square eta by 4 y cube Rayleigh number f prime f double prime, then we have plus alpha square by 2 y cube Rayleigh number A prime square, then we have the viscous term minus alpha by nu by y cube Rayleigh number f triple prime, and we have alpha nu by y cube, okay, Rayleigh number into theta. Okay. So, you can see this term you have g beta T w minus T infinity, and we have written your Rayleigh number in terms of Rayleigh number, and accordingly we have written this alpha by y cube. Okay. So, this way we have simplified it. Okay. You see Rayleigh number is your g beta T w minus T infinity y cube by alpha nu, right. So, alpha nu we have multiplied in the numerator and y cube we have divided. Okay. So, now you can see these two terms will get cancelled, this term and this term. Now, you can write this equation, divide both side by alpha square by y cube Rayleigh number y. So, if you divide by this, then first term what you can write? So, you can see it will be minus 3 by 4 f double prime. This term if you see, so it will be plus f prime square by 2. In the right hand side, the first term you can see. So, we are dividing by alpha square. So, it will be 1 alpha will come in the denominator. So, nu by alpha. So, there is a minus sign into f triple prime, and also we have nu by alpha into theta. Okay. And you know the definition of Prandtl number, it is nu by alpha, right. Prandtl number is equal to nu by alpha. So, if you put it here, so you can see it will be minus 3 by 4 f double prime plus f prime square by 2 will be Prandtl number into minus f triple prime plus theta. Okay. So, if you write in this way, so it will be 1 by Prandtl number into f prime square by 2 minus 3 by 4 f double prime. Okay. And in the right hand side you will have minus f triple prime plus theta. So, you can see that choosing the similarity variable, we could convert the three partial differential equations, continuity equation, momentum equation and energy equation to ordinary differential equation. So, if you see that using the similarity approach, we could convert the momentum equation, which is your partial differential equation, to ordinary differential equation. You can see this is a third order differential equation and it is non-linear, because you can see this is f triple prime. So, this is third order and you have f into f double prime, that means it is non-linear. Ordinary differential equation. But here you can see in this ordinary differential equation, in the momentum equation also you have term theta, which is your temperature. Okay. So, that means this equation also will depend on the temperature profile. Okay. So, what are the boundary conditions now? So, for a vertical plate, if you see, so this is your x, this is your y, right, and ambient you have T infinity and this is your T w, which is uniform. Okay. And there will be hydrodynamic boundary layer like this, okay, which is your delta. At any location you can find what is the delta. So, now you can see what are the boundary conditions. So, So, you can see at x equal to 0 you have no slip boundary condition, that means u is equal to 0 and v is equal to 0. Okay. So, that means at eta is equal to 0, if you put u is equal to 0. So, you can see the u scale. So, you can see from here. So, here you can see that if u is 0 then f prime will be 0. So, let us say that at eta is equal to 0. So, first find v is equal to 0. So, if v is equal to 0 then you can see from this expression, if v is 0 from this expression f prime will be 0. Okay, from this expression f prime will be 0. So, you can see it will be v is equal to 0, it will be f prime is equal to 0. So, if f prime is equal to 0 then for u is equal to 0. So, u is, this is the expression. So, f prime is already 0. So, f will be 0. Okay. So, this is the stream function actually. So, you are putting stream function value as 0. Okay, because it is a vertical plate. So, u 0 will give the stream function. Okay, and vertical plate you can see it is a stream line, and along a stream line your stream function will be constant. So, f is equal to 0. So, and x tends to infinity. So, near to this edge of the boundary layer obviously you will get the velocity 0. So, that means again you have v is equal to 0. Okay. So, you have v is equal to 0. So, at eta tends to infinity you will get f prime as 0. Okay. Now, you can solve this ordinary differential equation using these boundary conditions using some numerical technique, and you can find the velocity distribution. Okay. But you cannot solve it alone, because along with this you need to solve the energy equation. Okay. Because theta is involved. So, you have to solve in coupled way. So, you have to apply boundary condition for velocity in this equation, and when you will solve the energy equation you need to invoke the temperature boundary condition, and together numerically you need to solve these two equations, and you will find the velocity distribution as well as the temperature distribution. So, if you see that when we wrote the governing equations for flow over vertical plate when with uniform temperature boundary condition, what are the assumptions we took? Obviously, it is two dimensional, steady and laminar flow, and we have invoked the Boussinesq approximation, and you can see the properties like thermal conductivity, specific heat and the viscosity are constant, and the ambient temperature T infinity is also constant, and Tw which is your wall temperature, that is also constant. So, in the next class we will solve the energy equation, and we will convert this partial differential equation to ordinary differential equation using the same similarity variable. So, in today's class first we wrote the non-dimensional form of the boundary layer equations for natural convection over a vertical plate. So, we have introduced with two non-dimensional numbers, one is Grashof number, which is the ratio of buoyancy force to the viscous force, and another non-dimensional number, that is Richardson number, which is defined as Grashof number divided by Reynolds number square. This actually gives the ratio of buoyancy force to the inertia force. So, depending on the value of Richardson number you can see which is the dominant force. So, for Richardson number much greater than 1, obviously you can neglect the forced convection, it will be purely natural convection. If Richardson number much less than 1, then you can see that inertia force will be dominant, and you can have the forced convection, and effect of natural convection you can neglect. But when Richardson number is equal to 1, then both are significant, natural convection as well as forced convection. So, this is known as mixed or combined convection. Then we have used the similarity transformation approach, and using the similarity variable eta, and we have defined a velocity v from the scale of velocity v. We converted this momentum equation, which is your partial differential equation, to ordinary differential equation. So, first we found the stream function from the velocity v, and once you know the stream function, from there we found the velocity u and the velocity gradient del v by del x, del v by del y and del 2 v by del x square. So, all those terms if you put in the momentum equation, then you could get third order nonlinear ordinary differential equations. And the boundary conditions already we have discussed, that at the wall you have velocity v is equal to 0, which will give f prime is 0, and at the wall again u is 0 and it will give stream function as 0. So, f is equal to 0, and as eta tends to infinity, that means v will be 0 and f prime will be 0. So, in the next class we will derive the ordinary differential equation for the energy equation. Thank you.